Okay, today we're going to talk about how we would actually do this kind of stuff in the real world. Systems of equations and related ideas, when they come up in like real world applications, not like the sort of goofy little word problem type things that we see in class, but real applications where you actually use these things, it's generally a very large system with a lot of things, right? A lot of information. So this might come up in, like statistical analysis of like a big data set, that kind of thing. So you can think about something like predicting student success, right? So the university's got, I don't know, 3,500, 4,000 students, something like that. And for each of you, there's a whole bunch of data we have, right? Age, gender, ethnicity, socioeconomic status, high school GPA, placement test scores, ACT, like all of these other things, right? That can all kind of be used together to like build this big data set. Well, that means you've got, what I say, 4,000 students, 4,000 equations, right? Each of which has, 20, 30, 50, whatever, like bits of information, right? It's not exactly like solving a system, but it's basically the same kind of like process or like structure. So obviously nobody is going to like sit down and start doing hand calculations with something like that, right? So what we do instead is figure out a way to turn it into something that a computer can deal with, and then tell the computer how to go do a bunch of arithmetic, because computers are stupid, but they're really good at adding and subtracting. So like we make it go do it, and then just spit out an answer to me and tell me what it is, right? And the way we do that is with a thing called a matrix. We are just going to get kind of a like quick sense of what matrices are and how they work. The sort of full picture is like much bigger, right? It's like a junior level full semester course type of thing to like really kind of get the full picture of what's going on. But we're going to just kind of dip a toe in the water. So a matrix is a rectangular array. It's an object. In computer science, they call them arrays, but it's the same idea. Where we take a bunch of numbers and put them in a box. They're arranged into rows and columns. Rows go this way. Columns go this way. So this one has 2 rows and 3 columns. So when we talk about the dimensions, we call it a 2 by 3. 2 rows, 3 columns. Rows first, then columns. Each individual thing, of which there are 1, 2, 3, 4, 5, 6, is called an element or an entry. So this particular matrix has 6 entries arranged in 2 rows and 3 columns. What we are allowed to do with a given matrix are a few things that we call row operations that basically give us a way to just sort of dress it up differently without changing fundamentally what it is or how it works, right? Kind of like, I can write the number 4 as 8/2 or something, and like it's still the same thing, right? It's kind of the same idea. Row operations give us a way to rearrange or change the like form of the thing without changing the structure. So the row operations that we can use are swapping 2 rows. So the order doesn't matter. It doesn't matter that they're written like that rather than like this. So I could write -1, 2, 0, 3, 1, -5, and it would be the same thing, right? So I can swap. We can add or subtract 2 rows together and then use the result of that to replace one. So I can add those together, add the entries. So 3 plus -1 would be 2, 1 plus 2 would be 3, -5 plus 0 would be -5. That new thing, that new row, I can use it to replace either of the 2 that we started with, and that's still okay, right? It's still the same thing. Or we can take a row and multiply or divide by a constant. So like scale the whole thing, right? Multiply everything in row 1 by 2, for example. And again, it doesn't change anything. Do those things sound familiar? They're the exact same things that we've been doing to set up and do an elimination to solve a system, right? We haven't really done anything where we've, just said like, hey, I'm going to swap the order of these, but you can, like, it doesn't matter. We also haven't done anything where we cared about which one was the top line and which one was the bottom line. It's the same system if you swap them. Adding and subtracting two together, we've done a ton of that, right? That's our like main tool for doing elimination. And sometimes we also multiply or divide by something to get the coefficients to line up, right? So these are just the same operations we've been doing for elimination. So really all we're saying is that those work inside a matrix like this and don't change anything in like an important way, just like they don't change anything in an important way for a system, unless I can do it in a way that is helpful to me, right? To get it into like a form that is more useful. Same idea here. Okay, so take this matrix that I just gave you at the top of the page. For heaven's sake, where is it? 3, 1, -5, and -1, 2, 0. What we're going to do is rewrite it, replacing row 1 with the sum of row 2 and row 1. So the way that we, the like notation that we use to indicate a row operation like that looks like this. I'm going to replace row 1 with row 2 plus row 1. So I'm going to find the sum of those. I'm going to add them together, and I'm going to use that to replace row 1. That means I'm not doing anything to row 2, which is why I filled it in here for you, right? It's not going to change. Row 1 is going to change. And the way it's going to change is that I'm going to do, whatever operation that says to do. So if I take row 2 and row 1 and add them together, what do you get? 2, 3, -5. That's the new row 1. And again, just think of it just like taking two equations and adding them together and adding term by term, right? The like term thing is based on where they are now, right? So we're within the column, right? Those are the things that go together, adding these together. So 3 plus -1 is 2, 1 plus 2 is 3, -5 plus 0 is -5. Everybody okay with that? Yeah, okay, cool. All right. Same original thing. Do that one. Row 2 is 3 row 1 minus row 2. Okay, I would probably, maybe do a little scratch work on the side here. We're going to take row 1 and multiply by 3. So 3 times everything here would be 9, 3, and -15. Minus row 2. So I'm just going to copy row 2 down. -1, 2, 0. And we are subtracting. So again, I'm just doing some scratch work on the side so that I'm not trying to keep too many things in my head at the same time and, make some goofy arithmetic thing somewhere. So row 1 times 3 minus row 2. 9 minus -1. 3 minus 2 and -15 minus 0. So 10, 1, -15. did. 3 row 1 minus row 2. Okay. I'll be all right with that. Yeah. Okay. Okay, cool. All right. So what does this have to do with systems of equations? So if I take a system, and we've been doing sort of pretty much all of these, just about everything we've looked at, I've laid out so that everything is kind of arranged in the same order, right? Everything's in the same spot. And sometimes if they're missing terms with like the 3x3s and stuff, that makes things look like the spacing look a little funky, right? But we're preserving the order. The reason I'm preserving the order, one, so we can look at it and see how things line up. But two, if I know the order, then all I really need to pay attention to are how many of each thing that there are, right? So if I know these are both the x terms, I don't really need to worry about the x part. I just need to worry about, well, there's 5 here and 2 there. So if I'm going to do some kind of elimination thing, I'd have to take them both up to 10, and then I do that, and then I go on, right? Or, these are both y. Well, okay, there's 2 and -1. So, oh, hey, I can multiply this one by 2, and then we're good to go, right? The way we make this work then to, put it into some kind of a context that I can like write a program to deal with and tell a stupid computer to do the arithmetic for me, right? Is I preserve the order, right? So this is all the x stuff. This is all the y stuff. This is all the like right-hand side of the equation, or the constant, or however you want to say that. That's just a number. So if I've preserved the order like that, then what I really need to know are how many of each one there are. So I just take the coefficients and set up what's called an augmented matrix, or a matrix of coefficients, like this. 2 equations means that the matrix is going to have 2 rows. 3 things, right, x and y, and the numerical part means that the matrix is going to have 3 columns corresponding to, well, the same 3 things, x and y, and the right-hand side of the equation, the numeric part. As it's technically an augmented matrix, this little dividing line thing is sort of a subtle difference that we don't really care about. Just think of that as going where the equal sign goes. So we've got things arranged in columns with the x values and the y values, and then equal to the other side of the equation. This array, again, like computer programming languages and stuff, are set up so that they can interpret an array very easily, right? So these numbers that I peel away, I don't need to tell the dumb computer that can just do arithmetic that these are x and y and whatever. I just need to give it these numbers, and then it'll do the arithmetic part for us. Okay, so here's a system. What would this look like if I wrote it down as a coefficient augmented matrix? Okay, what should we put in that missing entry? 0, because there's 0 y. Yep. Yeah, there's got to be something there to kind of fill the space, but there are no y's, so 0 y. Good. Okay, now think about what actually, let's think about the system of equations first. If I was going to solve that, what could we do? Negative 2x is 6, right? So what's x then? Negative 3. Right? So it's 2 equations. 2 equations. I don't know what x and y are, but like I almost know what x is, right? I don't need to really do like a substitution or do an elimination or anything, because one of them has a missing thing already, right? So that missing term is actually helpful. And then once I get that, I can plug back in figure out what y is, right? That means if we're looking at the matrix form, the matrix representation is the same thing. Missing terms here are a good thing. That means zeros here are a good thing in kind of the same way, right? Because if I started with this and think about, okay, well, I'm solving a system that this thing represents, this tells me that x is -3, or, -2x is 6, so then x is -3. And then I can, back up and substitute and find the other thing that goes with it, right? So zeros are a good thing when they show up, kind of in this block, because that's missing stuff. That's information that I have, right? Really, that I have like a more complete picture than I think I do, maybe. Okay, so what about the next one? There's a matrix. How would you write it as a system of equations? And 0 plus y, so just y, equals 4. Well, again, if I'm trying to solve, we're already halfway there, right? Y is 4. So, okay, x is whatever x is to make the top line true, right? But we've got half of the answer already. So what we do with stuff like this then is we take our system, whatever size it is, we line everything up in order, we peel all the coefficients away and set up this matrix, and then we throw it into a computer and give it a program, some instructions, and say, hey, make it look something like this, so that I can read off the answer, basically, right? This sort of shape here, this like lower triangle with ones down the diagonal and 0 underneath, is called row echelon form. The main diagonal is the one that starts in the top corner in the first entry and goes down from there. So ones all along that diagonal and zeros underneath. Well, whatever size that thing is, then, think about like a bigger example. Some other things filled in all these other spots. The last row is going to look something like that, which means the last row I get to just read off part of the answer, right? Because this says 1z or whatever equals whatever this is. I know I've written that in the place where this last row would say 0, 0, 0, 1 of the last thing equals, 5. Well, okay, that's part of the answer. And then I can start working my way back up to find the rest of it, right? Just like we would do here in this sort of smaller case. So that's row echelon form. Look at the next one. And tell me what that would look like as equations. Like what information is there?
That would be something like what? X equals 7, y equals 2, then no.
Yep.
And then y equals
Z, yeah. Yeah, if I'm using x and y and z as the labels, then that's x is 7, y is 2, z is -3. So I can just read the answer off then, right? Like here, I would need to take this and kind of back up and substitute and do a little bit more work, right? Here, I can just read the answer off because I've got the ones down the diagonal, I've got zeros underneath, but I've also got zeros sort of everywhere else, right?
There's 3 terms.
This 0 everywhere else thing, the ones down the diagonal still means row echelon, but zeros everywhere else, call that reduced row echelon. Because that's kind of as far as I can take the thing, right? So the way this works is that, if you have some kind of program that lets you deal with matrices, right? So your calculator has a lot of this stuff built in, or any sort of computer like algebra thing is going to have this stuff built in. And row echelon and reduced row echelon are going to be like built in like commands, right? So if you go into the matrix little menu thing in your calculator, there's going to be a command that says reduced row echelon. And what it's going to do is take whatever matrix you give it and start adding and subtracting rows together, right? Doing those row operations. And it's going to stop once it gets here, right? One's down the diagonal, zeros everywhere else. Then it's going to say, oh, hey, here's your answer, right? X is 7, Y is 2, Z is -3. That's it, right? Because again, all it is a whole bunch of addition and subtraction. And, computers need to be told what to do. But once you tell it to do a bunch of addition and subtraction, it can do it really fast, right? Okay, cool. So this like process, right? Handling all this stuff, this is called either Gaussian elimination or Gauss-Jordan elimination. Difference isn't really anything that we need to be worried about. These are people's names. Gauss was a German guy who did a ton of math stuff. He's called the Prince of Mathematics, which is fun. And Jordan's another old dead guy who did a bunch of math stuff. This is worthwhile, so just indulge me for a second. He's the Prince of Mathematics. Now I know this looks like a real picture, but what I did is I took a picture of Prince and I took a picture of Gauss, which is like a drawing of Gauss, and I photoshopped them together. And I know you can't even tell. It's seamless. I know. He's the Prince of Mathematics.
Should have taken the Fresh Prince of Bel Air too.
Well, yeah, I mean, I guess, but right, yeah, that threw you off. Yeah, I get. It's not perfect. Maybe I'll try it again. I'll get AI to do it for me now.
Graphic design was the major.
Right. Yeah. Exactly. Okay. So let's see how this works. The thing I want you to keep in mind is that we're doing all of the same stuff that we've been doing, right? Elimination type stuff. We're basically just keeping track of things a little bit differently, right? So we've introduced this idea of a matrix to represent the thing. We're using row operations in place of like adding the equations together. It's really the same idea. Because it's new and the notation is new, it looks a little bit like intimidating at first maybe, but once you get the hang of it and start to realize like, oh, I'm doing the same thing. All I'm really doing is writing down less than I would have to otherwise, right? Because I'm not writing 3x plus 2y, I'm just writing 3, 2, So take this thing and write down a matrix that represents the system. How many rows?
2,
And how many columns?
3,
And what's the matrix look like?
2, 2,
2, 1, 5,
3, 2, 7.
3, 2, 7. Okay, cool. For the sake of doing it, I'm going to take this thing all the way. We're going to take this thing all the way down to the reduced row echelon version, just for the sake of like practicing with the row operations. In practical terms, if I'm trying to solve by hand, I would probably do like half of this maybe and then jump out. And we'll talk about that when we get there. But that means that my goal is going to be to make this thing look something like that. I don't know what these are yet, because if I did, I wouldn't have to do any of this. But what I want is ones on the diagonal, zeros everywhere else.
We could do elimination.
So I'm going to start with doing an elimination, and I'm going to start by looking at that term. So the thing about this that can get like a little bit weird is that when you combine these rows together, you can like do a thing and then undo the thing, if that makes sense, right? You can like eliminate something and then uneliminate it if you're not careful. So I'm going to start by trying to get a 0 in that lower left spot. So if I'm thinking elimination and trying to get rid of that first, what do you see that we could do?
Could you make the y equal to 2y and multiply it?
Okay. So multiply. Yeah, I'm gonna work on, if you're gonna work here first, I'm gonna think about eliminating this, so I'm just gonna kind of ignore everything else for the moment. 2 and 3, I would need to take them up to 6. So multiply the top row by 3 and the bottom row by 2. So 6, 3, 15. 6. That's not a 6. 6, 4, 14. You don't want to get rid of that guy. So we scaled everybody to make a match. I didn't really need to multiply this one by 3 necessarily. So if you're comfortable with like sort of going off to the side and doing that, like that number 2 we did on the first page, then that's fine too. Like I don't need to actually change what's in row 1. Now to get rid of that 6 in the lower left, subtract. So I'm going to leave row 1 alone. But I'm going to subtract. And I'm going to replace row 2 with row 1 minus row 2. Six minus 6. 0. Which is good, because that's what I was trying to do, right? I wanted to eliminate that entry specifically. So 6 minus 6, that does it. 3 minus 4, -1. And 15 minus 14, 1. Okay. Now, what do we know? What did we just find out? What does that row tell us? Negative y is 1, so y is -1. Okay, so if what I'm trying to do is solve the system, I could jump out at this point, right? Say, okay, well, I've gotten kind of what I needed to from the matrix thing, right? I know that y is -1. And I could back up and say, okay, y is -1 and figure out what x is, right? Kind of go like old school and just back substitute and figure it out from there. Is everybody tracking with that? Okay. For the sake of doing it, right? This is going to seem like I'm being a little pedantic, but for the sake of doing it, I'm going to keep working in the matrix to like reduce this thing down further, right? Just so that we've at least done it once. Yeah.
I'll make a test question. Would I have to do that, or can I just solve?
On like a test question, I'm not going to make you do it anyway. So
Oh,
yeah,
great.
right. So yeah, you could back out now on homework and stuff. I think there are a few that ask you to actually like give the like reduced version of the matrix. So you need to kind of keep going. All right, so just real quick, I'm going to take this thing and just flip that sign on the bottom thing. Again, just for the sake of going after this like reduced row echelon, very specific thing, right? So -1 times row 2. All right. Next thing I'm going to go after is eliminating that. Row 2 is kind of where I want it, so I'm not going to do anything with it. But if I want to eliminate that 3 that's sitting above a 1 here, we're going to multiply this by 3 and then I'm going to subtract. So I'm going to replace row 1 with row 1 minus 3 row 2. And just for the sake of time, I'm going to just go ahead and like do it. So 6 minus 0, 3 minus 3. Again, that's the thing I wanted. And then 15 minus -3. So 15 plus 3. And then very last thing, and again, it's because I'm trying to go specifically for that reduced row echelon thing. I'm going to take row 1 and divide by 6. So that's the reduced row echelon version of this matrix that represents this system. What does it tell us? What's the solution to the system? X equals 3, y equals -1. Okay. Now again, I know because, it's unfamiliar, right? Because it's new. This kind of seems sort of bizarre, right? Like this is a thing where, seems like I'm up here doing some kind of sorcery or something. But really what we're doing is the same kind of stuff we've been doing. We're just keeping track of things a little bit differently, right? And again, I, am being like a tiny bit pedantic and like going after this thing specifically, which isn't necessarily the only thing I could use to solve the system, right? But like row echelon, reduced row echelon have some other like applications. So that's why they're a thing. Okay, questions about that? B would be a very similar sort of thing. 7 and 8 on the back, same idea, but bigger systems, right? So this has 3 equations and 3 unknowns. If I'm going to write it down as a matrix, what would it look like then?
One, 1, 2, 17. 1, 2, 1, 16.
Bless you. And we would do the same kinds of things to reduce it down. I would work on these first, eliminating those. And then once those are gone, I would work on eliminating this. And then if I feel like cleaning up the like upper corner, then I would do that afterwards, right? The reason for sort of going in like an order like that is so that I don't end up doing something and then undoing that thing, right? So because I'm adding and subtracting rows together, if I like take row 2 minus row 1 and eliminate this, but then I combine row 2 and row 3 somehow, maybe I've uneliminated, right? I bring it back in. Yeah, Noah.
So, could you, to get the row echelon, the reduced row echelon, can't you just roll part of it, like you were saying before, then go back out, and then get the equation, and plug it back into the matrix?
Sure. Yeah. So yeah, you could do kind of a hybrid thing where like, think of, a sheet of paper with a big line down the middle. On one side, you've got the equation version. On the other side, you've got the matrix version. You could like jump over here and do some work and then jump back and then do some other work and then jump back. Yeah, like that all works, right? They're all equivalent. What most sane people would do though, is take this thing and say, well, that's going to be about as much fun as solving a 3x3 by hand is, right? Which is to say, like it's going to be kind of tedious and kind of a lot. I had this professor in undergrad who was like a little bit older and Ukrainian, I think, and I feel like he had like defected from the Soviet Union or something. But at some point, he gave us a like quiz problem in class that was a 4x4 like this, and we had to do, it wasn't exactly this, but basically the same thing. And it just ends up being like 2 pages worth of like really, dreary arithmetic stuff. And I remember thinking at the time, like, this feels like a lot, really. But here we are like 20 years later and I'm still talking about it. So what any sane person would do is take this thing and say, well, I know how to use a computer. We live in the future. So I would go to the internet and, oops, I already Googled it. I would Google something like matrix calculator and press enter and then click on like the first thing that comes up. Your graphing calculator has this kind of stuff built in as well. And the kinds of functions that are built into the calculator, among them is going to be some kind of fine row echelon form kind of thing. So what I'm going to do is just take this matrix and type it in. There we go. So 1, 0, 1, 8, 1, 1, 2, 17, 1, 2, 1, 16. So there's a matrix button somewhere, and in there's a like menu, and there's a command that says like REF or RREF. That's That's row echelon, reduced row echelon. If you want me to actually like show you how to do it, I can do that. That's fine. Yeah, REF is row echelon form. RREF is reduced row echelon form. But whatever it is, you put it in, you push the button, and ta-da. This one, I mean, I really did like just Google it and click on the first thing. I didn't like vet this beforehand. I saw it in the last class, but this one, for some reason, doesn't reduce this last row down, but look at what the last row says. -2z equals -10. So z is 5, right? So like I can reduce that down. And then once I've got z, I can back up and find y. Then I can back up and find x that goes with it as well, right? So what that says is that z is 5. And then the next row says that y plus z is 9. So y plus 5 is 9. So y is 4. Excuse me. And then the top row says that x plus z is 8, which means that x is 3. So our solution sorry, excuse me. 3, 4, 5.